I'm Luke, and today I'm going to tell you about how to build automated verifiers for systems code using Serval. So, low-level systems like operating system kernels and security monitors are often very difficult to get right, and developers can easily introduce bugs, which can compromise the entire security of the system. And because of this problem, recently we've seen many successful examples of how to apply formal verification to systematically eliminate bugs from these types of systems. And this has the great advantage that it provides strong correctness guarantees about these systems. However, it often requires significant effort on the part of the developer, usually in the form of manual proofs. One example of this is Certicos, which has about 200,000 lines of proof. And these systems can often take multiple person years to develop. So one approach to system verification that reduces the developer burden is called automated or push-button verification. And the high-level idea here is that the developers will write an implementation and a specification of their system and feed them as input to a tool called an automated verifier. The automated verifier converts these inputs into an SMT formula that can be given to an SMT solver, which will tell the developer if the system is verified or not. And this has the advantage that it requires no proofs on the implementation code. However, it places some restrictions on the types of implementations and specifications you can verify. Specifically, it requires that the implementation be free of unbounded loops, and it restricts the types of specifications you can write to be those expressible to an SMT solver. And an example of this is our prior work on the hyperkernel. Now, this approach still has several open challenges. First is that the automated verifier is often a very complex part of this verification stack. So how can we lower the effort of writing automated verifiers and make them reusable for other purposes? Second, like any verification approach, things don't always work out the first time. So when things go wrong or in their verification performance bottlenecks, how can we find and fix these problems so that we can verify the systems we want to verify? Finally, given this automated verification technique, how can we apply it to systems, implementations, and specifications that weren't originally designed for automated verification? So today in this talk, I'm going to be describing Serval, which is a framework that we developed that makes it easy to rapidly prototype and develop automated verifiers. It's easy enough, in fact, that as part of Serval, we've provided verifiers for 4 different low-level languages. To develop these verifiers, we also created the idea of a symbolic optimization, which is a way of systematically scaling the automated verifiers to work on actual systems. And to understand the trade-offs that this approach has compared to other verification techniques, we report on our experience with retrofitting existing systems to be verified using Serval. And to show that our verifiers are general and can be used for other purposes, we've also were able to find 15 new bugs in the Linux kernel's BPF JIT using the verifiers. So one assumption we make, which is similar to previous verification approaches, is that we make no guarantees on concurrency or on side channels. So first, let's see a high-level overview of how developers can use Serval to verify a system. As input to Serval, the developers write a system specification, and it provides the system implementation in the form of a RISC-V instructions. The RISC-V verifier is provided by Serval, and its job is to convert the RISC-V instructions into symbolic constraints that can be reasoned about for verification. Serval itself provides libraries to make it easier for developers to write system specifications, and provides libraries that help the RISC-V verifier scale to real systems code. Serval itself is implemented in Rosette, which is an extension to the Racket programming language that provides the support for verification tasks and an interface to an SMT solver. Ultimately, the SMT solver is responsible for discharging the verification conditions. So now, to make this more concrete, let's look at a specific task that a developer might want to use Serval to verify. So on the left here, we have an example. We have a specification of a simple sign function written in Rosette. So this sign function takes an integer, checks if the integer is negative. If so, it returns -1. If it's positive, returns +1, and returns 0 otherwise. So after writing the specification, the developer then implements this sign function in some language and compiles it to a series of RISC-V instructions. Now, in order for Serval to verify that this RISC-V instructions have the same behavior as the specification, it's the RISC-V verifier's job to turn these instructions into something that can be reasoned about. So next, we're going to see how this RISC-V verifier is built. So verifiers in Serval are built in a three-step process. So first, you write a verifier verifier for a language as an interpreter for that language written in Rosette. Then, you apply that verifier to your task and use a process called symbolic profiling to find verification performance bottlenecks that arise during verification. Once you've found the verification performance bottlenecks, you can apply what's called a symbolic optimization to fix the bottleneck and speed up the verification. And the developer will repeat this process until verification succeeds in a timely manner. So, to get a concrete idea of exactly how this process works, let's step through a simple example, which is a subset of the RISC-V verifier that is provided by Serval. So here on the left, what I have is a subset of the RISC-V verifier provided by Serval written in Rosette. And as you can see, it's written as a normal CPU interpreter. So it has a struct, which contains the machine state of the system, including the current program counter, general purpose registers, and other system states such as memory. To interpret an instruction, it obtains the current program counter of the system, fetches the instruction at the program counter, and then looks at what type of instruction it is so it can correctly implement the instruction semantics. And this has the advantage that this type of verifiers are easy to write because developers are used to writing interpreters like this. And secondly, it allows us to reuse existing CPU test suites, such as the RISC-V standard tests, to improve our confidence that the verifier is correct. So, now that we've seen what the verifier looks like, let's go back to the example of the developer trying to prove the sign function. So, with the verifier in hand, the developer now can ask Serval if this implementation of the sign function correctly satisfies the specification. If everything works, then the developer is happy, and they've proven that this code is correct. However, oftentimes with automated verification techniques, verification can be slow or can even time out. And this process can be very frustrating for the developer, as it might be difficult for the developer to understand why this timeout is occurring. So, with normal programming, when you have performance bottlenecks, you might use a tool like a profiler to figure out where issues are in the code. And analogous to that, Rosette provides a tool called Symbolic profiling, which will tell you pieces of the code which can be expensive for symbolic evaluation. So what I've shown is an example of the Symbolic profiler's output for this particular interpreter and the code that we're trying to verify. And you don't have to understand all of the details of what it's reporting, but the key idea is that it's telling us that one of the expensive functions that's expensive for symbolic evaluation is the instruction fetch. So in order to get a deeper understanding of what's actually causing this verification bottleneck, let's go back to look at our interpreter and the code that we're trying to verify. So again, we have our interpreter in Rosette and the RISC-V program. And the problem here has to do with this RISC-V, or with the fetch instruction for RISC-V. Now, to understand exactly what's causing this issue, I have to explain a little bit about how symbolic evaluation works. Symbolic evaluation works in Rosette, like in other tools, by systematically and exhaustively testing all possible paths through the program. So to avoid there becoming too many paths, Rosette also merges states back together at the control flow join points. So to make this concrete, let's look at the first instruction of the RISC-V program. The first instruction, SLTZ, is a RISC-V instruction that checks if if the register value of A0 is negative, and if so, sets A1 to 1. On the left, we have a symbolic evaluation graph, which is a visualization of the execution of this program. At the top is the initial state, where the program counter is 0, and each of the two registers is bound to a symbolic integer. Of course, with this program, there are two cases. Either the value in A0 is negative, or it's not. And so Rosette splits execution into two states, one where it sets A1 to 1, and one where it sets A1 to 0. And then it merges the states back together into a single symbolic state that summarizes the execution. And this approach works well for this function because it's kept the total number of states to 1. Moving on to the next instruction. The next instruction is in RISC-V is a conditional branch which branches if the value in A1 is not equal to 0. And similar to the behavior for the first instruction, this instruction has two cases. And Rosette will branch on whether A1 is non-zero, and then split execution into two states. Again, it will merge the results back together. However, because this instruction affects the program counter, the resulting merged symbolic state has made the program counter become symbolic. And the program counter becoming symbolic is an issue for symbolic evaluation. Because when we try and fetch the next instruction, if the program counter is symbolic, the interpreter has to conservatively consider all possible instructions in the entire program. In this case, this program only has 6 instructions, so it has to consider the program counter is any value between 0 and 5. But for a more complex program, the number of states might explode to be much larger. So how can we fix this particular issue? So one possibility is that we might consider adding an optimization to the SMT solver to be able to deal with this problem. However, optimizations to the SMT solver are too late because this problem is actually occurring during symbolic evaluation. So in order to fix this type of problem and others, we've developed the idea of a symbolic optimization, which you can think about like a peephole optimization that operates on symbolic state. And it allows the developer of the RISC-V verifier to have fine-tuned control over the symbolic evaluation process and where states are merged and split. And it lets the developer of the RISC-V verifier use domain knowledge about RISC-V to help improve the verification performance for real systems. And Serval provides a set of these symbolic optimizations that deal with patterns that are commonly found in systems code, like this symbolic program counter example, and others such as dealing with symbolic memory addresses. So, armed with this idea of a symbolic optimization, let's see how we can use an optimization to fix this bottleneck to deal with the symbolic program counter. Serval provides a symbolic optimization called split PC, which deals with the exact situation that we saw here. What split PC does is it matches on the symbolic structure of the program counter to find each possible concrete value that the program counter can take on. It evaluates the program separately using each concrete value and then merges the states together afterwards. And we can see the effect this has on verification performance by looking again at the symbolic evaluation graphs. So on the left, we have the old symbolic evaluation graph that has to try every single instruction in the program. With split PC, what it does is match on the structure of the program counter to see that the two possible values are only 4 and 2, which are the possible results of the program counter after executing the branch. And this reflects a 3x reduction in the total number of states that we have to explore, and that reduction would be even higher if the program were more complex. And the insight here behind split PC is that it allows the developer of the RISC-V verifier to use domain knowledge about RISC-V. In this case, it's that the program counter register should be split to avoid state explosion, that is, to avoid the states becoming too complex, whereas other registers should be merged to avoid path explosion, which avoids having to explore too many paths. So, in summary about the verifiers, a verifier in Serval is an interpreter in Rosette iterated upon with symbolic optimizations. And this means that the verifiers are easy to test because you can execute them on standard test suites. And we've provided a systematic way to scale symbolic evaluation when it's slow using these symbolic optimizations with profiling. Some caveats of this approach are first that symbolic profiling can't directly identify expensive SMT operations, such as nonlinear arithmetic like multiplication. And second, like regular profiling, it can give you an idea of where a problem might occur in the program, but it can't tell you what the fix is. So repairing these verification bottlenecks still requires expertise. Because Serval allows us to rapidly develop verifiers, Serval actually comes with verifiers for RISC-V, x86, LLVM, and BPF. So the two high-level questions we have about the Serval approach are first, is whether existing systems can be retrofit to be verified using Serval. And second, whether Serval's verifiers can be reused for other purposes. So to understand how we can retrofit existing systems to be verified using Serval, we ported the existing verified systems Certicos and Komodo to RISC-V. We retrofit the systems for automated verification, applied our RISC-V verifier directly to the binary image of the implementation, and proved functional correctness and non-interference similar to the original efforts. And this process took roughly 4 weeks for each of the systems. So what exactly do I mean by retrofit the systems for automated verification? To retrofit a system for automated verification, you have to ask 2 main questions. First is whether the implementation of the system is free of unbounded loops. This is a requirement for symbolic evaluation to encode the semantics of the program as an SMT formula. If it's not, then you have to find another way to implement the system, which potentially requires changing the interface, that allows you to implement it in a way that is free of unbounded loops. Second is whether the system specification is expressible in this subset of first-order logic that Serval uses. If it's not, you need to find an alternative way of phrasing your specification that is effectively decidable by an SMT solver. So to get a concrete idea of how this works, let's look at an example of how we retrofit Certicos for automated verification via Serval. Certicos is a verified OS kernel that provides strict isolation among a number of processes. It enforces a physical memory quota on each process and statically partitions the process ID space. Its specification uses a security specification called non-interference that effectively states that each process behaves as though it were the only one in the system. To retrofit Certicos, for the implementation, was already free of unbounded loops, so we didn't have to change the implementation. We didn't have to change the implementation or the interface in order for this to be amenable to automated verification. However, we did tweak the interface of the spawn system call to close 2 potential information leaks. For the specification, Certicos' original specification uses a definition of non-interference that's phrased over traces of system events of unbounded length, which is not expressible in the first-order logic that Serval uses. However, Certicos' original verification efforts proved this non-interference by breaking it down into 3 individual properties that hold over 1 action at a time. Together, these properties imply non-interference, and each of them is expressible in Serval, and so we reuse these 3 properties as our top-level non-interference specification. Of course, not every system can be verified, or can be retrofitted to be verified using automated verification, but we find that security monitors like Certicos and Komodo are good fits for automated verification, because they're free of unbounded loops, and they tend not to use inductive data structures that are difficult for SMT reasoning. Now, what I've just shown you is one possible way of using the Serval verifiers to verify refinement for these 2 systems. But these verifiers can also be reused and combined for other purposes. So to show that we can reuse them for other purposes, we combined the RISC-V, x86, and BPF verifiers to find 15 previously undiscovered bugs in Linux kernel's BPF-JET compiler. And each of these bugs has fixes and new tests have been upstreamed into the Linux kernel. And if you're curious about more details, you can read the paper. So in conclusion, today I've talked to you about how you can write automated verifiers using Serval by lifting interpreters into verifiers. And we've provided a systematic way for scaling symbolic evaluation to help you verify things when the verification performance is bad. And finally, I've showed you how to retrofit Serval to existing low-level security monitors like Certicos and Komodo. And hopefully the next time that you decide to verify a system, you have a better idea of the trade-offs that automated verification can afford. And for the paper and more info, you can visit that URL.
We have time for a couple of questions.
Hello, Matthew Milano, Cornell. Can you hear me all right?
Yep.
I guess I have a sort of high-level question. Serval is targeting a very low level of the end of the compilation stack for these systems at RISC-V and LLVM.
Yep.
When we have things like verified compilers from C down to certain assemblies, why did you choose to target that low level of the stack?
That's a good question. So first, one advantage of verifying directly at the RISC-V level is it allows us to use standard toolchains and compilers without having to trust the correctness of them because we verify the instructions that come out at the end. And secondly, the semantics of RISC-V and LLVM are usually simpler than higher level languages like C.
Thank you.
Hi, John Howell, VMware Research. So I've spent a lot of time thinking about verification higher in the stack where I think about inductive data structures and other inductive properties. Have you thought about how I might join these two things? Because I hate reasoning about fine-grained code, and it seems like you have a nice handle on that. Have you thought about how this might interact with higher level properties?
Yeah, so well, that's one thing we're interested in looking at in the future is how to connect the high-level guarantees that you can get from something like Coq or Daphne and connect it to these sort of lower-level, more first-order proofs that we can do in Serval. So we have some ideas about that, but it's still an open challenge for exactly how to integrate higher-level verification into this type of automated technique.
Thank you. Ken Berman, Cornell. So for fun, I spent a couple of weeks working with Ivy trying to prove a different kind of system. And I ran into the kinds of problems you were talking about with CentOS. I have a question about this. So, CertiOS. So in the step where you had a difficult proof and then it turned out there was a prior result that you could break it down as 3 subcases and you tackled the 3 subcases, you're relying on somebody else's proof that breakdown is adequate. Is that because that was a higher order property that they had to prove by hand, or how does one verify their reasoning, which you depended upon?
So that's a good question. So the high-level non-interference that Certicos uses is higher order and not directly expressible in Serval's verification logic. To prove that this sort of breaking down of it into these first-order properties is sound, you'd have to use like a higher-order tool such as Coq, which is what the original verification of the system used. So for some of these systems, what we did is actually we can prove on the side that using a tool like Coq that the 3 things that we prove do actually imply the higher level non-interference, but that proof is disconnected from the rest of the automated verification.
So could there be a kind of a soundness proof that you could develop that any Coq proof of a higher order property can safely be used
Maybe you
as
guys
kind
can
of an
take this
axiom
offline?
by Serval?
Maybe you guys can take this offline?
Sure.
All right, let's thank the speaker.